Periodic relationships among the elements. One of the most important activities is a search for order. So we're going to look at how the periodic table came to get the order that it is in today. In 1869, two scientists published classification schemes of known elements that closely resemble what the periodic table looks like today. Both showed a regular periodic repetition of properties with increasing atomic mass. Mendeleev arranged elements with properties in the same vertical column. So hydrogen, lithium, sodium, potassium, and so forth were similar because they reacted in a 1-to-1 mole ratio with chlorine. Beryllium, magnesium, calcium reacted in a 1-to-2 mole ratio with chlorine. At his time, there were only about 60 known elements, so Mendeleev left blank spaces for those elements that had not been discovered yet. When you look at the periodic table, some elements are obviously out of order. When we look at atomic mass, Te and I, for example, are out of order by atomic mass, but we arrange elements by atomic number, the number of protons, and by this group of repeating properties. So periodic law says the properties of elements are periodic functions of their atomic numbers. If elements are in the same group, they have similar electron configurations. For example, lithium, sodium, potassium. They're in the same group. Electron configurations end in S1, whether it's 2s1, 3s1, or 4s1. The electron configurations are responsible for the properties of elements, but this was not determined until much later when we came to get the electron configurations. The number of electrons in the outermost energy shell, which is the number of valence electrons, is equal to the group number for the A groups. So if I'm in group 1A, I have 1 valence electron. If I'm in group 4A, I have 4 valence electrons, and so forth. So we can use the periodic table to answer questions about electron energy states. For example, how many outer shell electrons are in an atom of bromine? Well, bromine is in group 7A, so it will have 7 valence electrons. How many 5p electrons are in tellurium? Tellurium's in group 6A, so it's going to have 6 valence electrons, but if I'm looking specifically at 5p, tellurium ends in 5p4. There's different ways that we can classify elements. Metals, nonmetals, metalloids is one classification scheme. And for this classification scheme, we look at the stair step. Metals are to the left, nonmetals are to the right, metalloids are right on the stair step. We can do S, P, D, and F block based on their electron configurations. Or we can do representative, noble gas, transition, lanthanides, actinides. Representative are the A groups 1 through 7A. Noble gas, group 8A specifically. Transition elements, the B groups right there in the middle of the periodic table. Lanthanides are the 4F series. They start with lanthanum. Actinides are the 5F series. They start with actinium. When you look at the periodic table, the stair step starts between boron and aluminum and continues down. Metals are to the left, including all these down here. Nonmetals are to the right. I'll go ahead and circle the metalloids. Aluminum's on the stair step, but aluminum is a metal. So I'm going to circle the metalloids for you here. Polonium is also considered a metal. So Al and Po are on the stair step, but they are considered metals. Effective nuclear charge. In a helium atom, the nuclear charge is +2. There are 2 protons. However, the full force of the +2 charge is offset because the two 1s electrons repel one another. So each electron feels a charge that is less than +2 because of this repulsion. We call it a shielding effect. So the effective nuclear charge, ZeFF, is given by Z minus sigma, where Z is the actual charge, and sigma is the shielding constant. We kind of draw a picture of helium here. Helium has 2 protons. I'm going to use the Bohr model because it's easier to represent here. but both electrons are on the first energy shell, on the 1s. Well, electrons repel one another because they're both negative. And so this is what is called shielding. The electrons shield one another. They repel one another. And so each electron doesn't feel the full +2 charge from the nucleus. So that's all effective nuclear charge is. It's how much positive pull does the outermost electron experience. That's what effective nuclear charge is. Let's look at lithium. I'll draw another picture here for lithium. Lithium has 3 protons. So the actual charge is +3. 2 of its electrons are on the 1s, and then you've got 1 electron that's on a 2s. Well, this electron out here on the 2s is repelled by the electrons on the 1s. And so effective nuclear charge for lithium is going to be +3 minus the shielding constant, which is 1.7. So the outermost electron in lithium experiences a positive pull of 1.3. So that outermost electron is held on by a positive 1.3 charge. Now there's an easier way to find this shielding constant. The 1.7 comes from experimental data, but the sigma, the shielding constant, is simply equal to, if I want to estimate the number of core electrons, the number of inner shell electrons. So if I want to estimate for lithium the effective charge that that outermost electron experiences, I would say +3, which is the number of protons, minus the number of core electrons, 2 core electrons. They're both on the 1s. And so that outermost electron for lithium would experience a charge of +1. Now this is an estimation, but that would be an easy way to estimate the amount of effective nuclear charge that's holding that outermost electron in. Atomic radius is a size of an atom. And atomic radii are determined by taking half the distance between 2 identical atoms in a diatomic molecule. As we move down a group, atomic radii increase because we're adding electrons to larger orbitals. So for example, lithium's in the 2s, sodium's in the 3s, potassium's in the 4s, and so forth as we go down group 1a. Well, as we keep adding orbitals from 2s to 3s to 4s, we're getting further and further from the nucleus. So the radius gets larger. Lithium's 1.55 angstroms, 1.55 times 10 to the negative 10th meters. Sodium's 1.9 times 10 to the negative 10th meters, and so forth. As you go from left to right across the periodic table, atomic radii decrease. They get smaller. We add an electron. We also add a proton as we go from left to right. The proton tends to pull the electron cloud in tighter, and electrons are all added to the same energy shell as we go from left to right. So the repulsion and shielding effects are small, but the additional proton makes the effective nuclear charge increase and pulls the electron cloud in tighter, making it just a little bit smaller from left to right on the periodic table. Here is row number 2, lithium, beryllium, boron, and so forth. And you'll see that, in general, atomic radii decrease from left to right. I know there is a slight increase from carbon to nitrogen, but in general, there's a slight decrease from left to right. And we're going to look at just the trends. What is the trend? Well, the trend is left to right, it gets smaller. The largest element in terms of radius is francium, if you want to remember it this way. Francium is the largest element, and the smallest element is in the upper right corner. Helium is actually the smallest in terms of atomic radius. So here's some examples. If you look at your periodic table, put these in order from smallest to largest atomic radius. Well, in this first one, Mg, P, Al, Ar, these are all in row 3. So if I want the smallest element in row 3, I'm going to look on the right. So argon would be the smallest out of these 4, and then P, and then aluminum, and then Mg. So that's the order for these 4 elements because they're all in the same row. Next example, beryllium, copper, zirconium, polonium. These are kind of scattered around the periodic table, with atomic radius, looking top to bottom has the larger effect. So I always look top to bottom before I look left to right. And if you look top to bottom, the one that's closer to the top, which is going to be the smallest, is beryllium. Beryllium is in row 2. It's by far the smallest. It's in row 2. Next would come copper. Copper's in row 4. Next, zirconium, row 5. And the largest, polonium, in row 6. So I always look top to bottom in the rows before I look left to right on the periodic table for atomic radius.